Okay, we are back. AP practice problems on the FTC page 3. This problem is, I think, hard, but it's actually very similar to the one we did in the video. So once again, I'm going to do this entire problem with explanations in under 15 minutes, which is the amount of time allotted on the AP exam for each one of these problems. Okay, let's go. What do we have here? We have a graph which I've drawn, and this graph is composed of lines. They say piecewise linear. That's the AP exam's language for that, and it is a graph of g prime. So again, we're going to reason on this entire page about this function g, but this function g is not depicted. What are we given? We're given a function which describes the rate at which g changes, and we're also given the value of g at 2. G of 2 is 5. So knowing that g of 2 is 5 and knowing the rate at which g changes, we can reconstruct the g function for any value that we need. Okay, good. Part A, find the x-coordinates of all points of inflection for the graph of g. Okay, so what are the points of inflection of g? Well, okay, now we've done this like 3 times now. Where does g have points of inflection? G is going to have points of inflection where g double prime, they do say justify, so you have to explain, where g double prime changes sign, or where g prime changes direction. So, I'll just write that. G has a point of inflection where the concavity changes, which is another way of saying where g double prime changes sign, or where g prime changes direction. And this is just another way of saying g prime changes direction, changing direction meaning changing from increasing to decreasing. Okay, and because we have access to a graph of g prime, perhaps it's most natural to just talk about the g prime graph. So what we can say is, by inspection, again, you don't really have to write this, but I like it. By inspection, so in other words, looking at the graph of g prime changes sorry, zoned out for a second. G prime changes changes direction at 1 and 4. Yeah. So good. Yeah. By inspection, G prime changes from increasing to decreasing at x equals 1, and G prime changes from changes from increasing to decreasing at x equals 1, and G prime changes from decreasing, to increasing at x equals 4. So, G has a point of inflection at x equals 1 and x equals 4. Boom. That is totally sufficient. You're using one of the alternative definitions of point of inflection, which is where G prime changes from increasing to decreasing, and there's a graph of G prime, so this seems like the best way to do this problem. Okay, B is, I think, really like the heart of it, so we'll do B right here. What does B say? B says find the absolute maximum of G on the given interval. And once again, the J word comes out, so we have to explain that means in full, complete sentences. Well, when does a function g in general have an absolute maximum? Answer, at the endpoint or at a relative maximum. So we need to compute g at the endpoints, and we need to compute g at the relative maximum. So let's just go. I'll even just write that, right? G has has an absolute max at an endpoint or at a relative maximum. Okay, does G have any relative maxima? Well, we know that a function has a relative maximum when the derivative changes from positive to negative. So we merely look at G prime and see where does it change from positive to negative. And there's only one place where this happens, which is at x equals 2. And so, though there are 3 times, okay, the sort of lame, slow way to do this problem would be to find all the critical values and check all of them. And what are the critical values? The critical values are anywhere where G prime is 0. Well, there are in fact 3 of those, right? Negative 1, 2, and 6. But only 2 is an honest candidate, because only at x equals 2 does G prime change from positive to negative, and therefore only at x equals 2 is there a relative maximum. Okay, so G has an absolute maximum at an endpoint or at a relative maximum. Good. And now we just say that G has a relative max at x equals 2. Only because that's where G prime, and if you want to even write by inspection, which is just saying, dude, I'm looking at the picture, changes sign from positive to negative. Okay, so you're asserting that the sign change in the derivative tells you where the function has a relative maximum, and you're noting that you're just looking at the derivative, so that's where it's happening, at 2. Okay, and now, if I want to find the absolute maximum, now I just need to compare G of 2 with these other values at the endpoints. Okay, so let's go. What is G of 2? Well, G of 2 is in fact just 5, so that was the problem, that was the thing given to us in the original problem. Okay, what's another easy one? I think another easy one to calculate is G of 7. What's G of 7? Well, now we bring out our full sort of theoretical understanding of the fundamental theorem of calculus. G of 7 is just G of 2 plus the integral from 2 to 7 of G prime. If you tell me if you want to know the value of G at 7, you just take the value of G at 2, and you look at the change in G from 2 to 7. And the change in G from 2 to 7 is just the integral from 2 to 7 of the rate at which G is changing. So maybe you're getting more and more comfortable with this. Okay, well, what is G of 2? It's 5. And what is the integral from 2 to 7? I can just do this in my head maybe. It's actually clear on the paper. This is a triangle of area 4 rather, because it's a base 4, height 2 triangle, so that's 4, but then we also subtract a little triangle of area 1/2, and so it's in fact just negative 3.5. So if this integral is negative 3.5, this integral from 2 to 7, then that means that G of 7 is just 1.5. Good. So that is G of 7. Okay, so sort of 2 down, 1 to go. The value of G at the right endpoint is 1.5. The value of G at 2 is given to us as 5. Then the last one is to compute G at the left endpoint, G of negative 3. Okay, and here's where there are sort of 2 ways to do this. In the previous video, what I said was, and you might prefer this, that if you somehow knew the value at negative 3, and you added the integral from negative 3 to 2 of G prime, then once again, the value at negative 3 plus the change in G from negative 3 to 2, which is just the integral of the rate at which G is changing, that this would give you G of 2. And okay, maybe it's just better to always be doing it this way. What do you get? Of course, well, you end up with that G of negative 3, so therefore G of negative 3 is, in fact, G of 2. Okay, I guess I'm just going to rewrite this, minus the integral from negative 3 to 2 of G prime. Okay, and let's just finish it off. G of 2 we know is 5, and what is the integral from negative 3 to 2? So I need to find the areas of these 2 triangles. Just doing this in my head because it's easy. This is also a triangle of area 4 because it's 2 by 4. So that's 4, but then this triangle has area 3 by 1. So that's like 1.5. And so this integral is negative 4 and 1.5, negative 2.5. So this becomes 5 minus negative 2.5. If you followed all that, I mean, I think you should, because it's just integration. This is the integral from negative 3 to negative 1 is negative 4, and the integral from negative 1 to 2 is 1.5. And so negative 4 and 1.5 is negative 2.5. And so in fact, what we get is 7.5. And so the answer is 7.5 is g of negative 3. Okay, well, is that good? Yeah, because I now am done, right? I've computed the value of g at the relative max, I've computed the value of g at the endpoints, and I get that the answer is 7.5, and so maybe now I just squeeze in the answer. So the absolute max of g on the interval negative 3, 7 is 7.5. That's what they want to know, the absolute maximum value. They even put the word in value, and we've justified it because we know it must occur at one of these special points. Notice that in this case it was at an endpoint, so it's very important that you check the endpoints because they could very well be one of the places where the function's maximum. Does this answer make sense? Yeah, it just does totally make sense. What is the value of g at negative 3? Well, okay, now I know it's 7.5. Previously I didn't know. But what I can tell you is that I lose a whole bunch of value, g does. From negative 3 to negative 1, g gets smaller. By how much does g change? In fact, it changes by 4, by negative 4. It goes down by 4. And then g goes back up by 1.5. So the very casual way of thinking and understanding, which is not what you should write in your paper, but it is a good way to think, is that on the interval from negative 3 to negative 1, g goes down by 4, and on the interval from negative 1 to 2, g goes up by 1.5. But overall, from negative 3 to 2, g has gone down. Therefore, since g has gone down, it's definitely going to be the case that g of g of 2 is less than g of negative 3. Because the function overall, the g function not depicted, got smaller from negative 3 to 2. Okay, and then from 2 to 6, the g function goes down again by 4, and then goes up by only a half. So overall, we lost 3.5 between 2 and 7. So sort of course, g of 7 is going to be less than g of 2. And that's in fact what we find, right? Okay, so all of these, sort of doing these computations is sort of the fastest, I think, way of doing the problem, but it certainly helps, I think, to also think out what's going on here. And okay, there's even a way of answering this problem wherein you say an alternative solution, which I'm not going to write down, but which is legitimate if you write it down very carefully, is to go through the logic of everything I just said. To say, simply, instead of actually explicitly computing g of 7 and g of negative 3, I mean, you sort of have to anyway, but you could, for example, say that, and this will come up more in the next problem, you could, for example, say that the integral from 2 to 7 of g prime is sort of just obviously negative. Or you could just compute it, and you could see that it's negative 3.5. Since it's negative 3.5, that means the change in g from 2 to 7 is negative, which is to say that g of 7 is less than g of 2. And if g of 7 is less than g of 2, then I don't even need to report g of 7, because it's clearly not the absolute maximum, because it's smaller than g of 2. I feel like that's more roundabout, and so on the AP exam answer keys and stuff like that, you will never see them going through this logic, because it's simpler, seemingly, to just compute g of negative 3. Okay, la 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 la, and then and g of 7. And you sort of have to do it anyway, because even once you determined that g of 3 was the absolute max, or even, sorry, once you determined that the absolute max occurs at negative 3, by, for example, arguing, as I have, that the integral from -3 to 2 is clearly negative, therefore g decreased from -3 to 2, and therefore that g of 2 is less than g of 3, and therefore, since the absolute max must occur at the endpoints or a relative maximum, that the relative max occurs at g of -3, you still have to compute g of -3 anyway, because you still need to report the final answer as what is the maximum value. Okay, extremely long-winded. I am not going to make the 15-minute cut this time, no way. Woo, but close. Because the last two parts are, I think, easy. Part C says, find the average rate of change of g on the interval -3, 7. Okay, we just did a problem like this, right? If I want the average rate of change of g on -3, 7, then ignoring for the moment in your brain that g is this complicated thing that I don't have access to, how do I just find the average rate of change of a function on an interval? Answer, it is just equal to g of 7 minus g of -3 all over 7 minus -3. In other words, it's the total change in the function over the total length of the interval, and I think we've just calculated all these things already. We have, what is g of 7? It's 1.5. What is g of -3? It's 7.5. And so that's -3/5. Yep. And so this is, on the top here, this is -6 over 10. So this is -3/5. Okay, so on average, well, this just makes complete sense, right? If we started at 7.5 and we ended at 1.5, g lost 6 of its value throughout this entire interval. But since the interval was of length 10, the average rate of change was -3/5. This all just makes so much sense. Okay, part D is a sort of a theoretical, kind of sneaky little gotcha question. It is so awkward, I think, their phrasing here. Extremely awkward. Here's what it says. Find the average rate of change of g prime. Okay, well already they're making us do some weird thing. This is the average rate of change of g. Now you have to find the average rate of change of g prime. And so suddenly this problem has nothing to do with g anymore. And the fact that g prime is a derivative suddenly becomes irrelevant. Because they just want us to find what is the average rate of change of this function. Okay, well, the average rate of change of g prime on the interval -3, 7 is, analogously, g prime of 7 minus g prime of -3 all over 7 minus -3. Okay, what is g prime of 7? Well, it's 1. And what is g prime of sorry, I'm just weirdly doubting myself for a second, but no, g prime of -3 is -4, and this is 10, and so we get 1/2. 1 second. The average rate of change of this function, yeah. So yeah, this is just designed maybe to really test if you can keep it all straight. And I am just barely passing right now. Yeah, we want to know. We have this function, and okay, yeah. So we have this function. It's so much more useful if you just don't even think about it as a derivative. Hey man, I got a function here. What is this function doing? Well, it's starting down at -4, and by the time I get to the end, it's at 1. So I got from -4 to 1, and in other words, I went up by 5. So this function increased by 5. How long did it take to increase by 5? It took 10 units of time. And so, therefore, my average rate of change is 1/2. Okay, now comes this follow-up gotcha question, which is, does the mean value theorem applied on the interval -3, 7 guarantee a value of c such that g double prime of c is equal to this average rate of change y or y not? Okay, they're just trying so hard to test the mean value theorem in some kind of way. And what does the mean value theorem say? It says there's always a point at which the instantaneous rate of change equals the average rate of change. But they are asking it about this g prime function. Okay, so what does the mean value theorem say? The mean value theorem, all right, how can I write this? If you apply the mean value theorem to g prime on the interval -3, 7. That is what is being proposed. They are proposing that you apply the mean value theorem to g prime on the interval -3, 7. Then what does the mean value theorem assert? The mean value theorem asserts that there exists a c on the interval -3, 7 such that the derivative of the function, okay, but now the function we're discussing is g prime. So in other words, such that g double prime of c equals the average rate of change of g, which is what we got, which is 1/2. Okay, so if the average rate of change of g prime is 1/2, the mean value theorem would say that there exists a point where the derivative of that g prime, otherwise known as g double prime, equals 1/2. And so a maybe normal person would just say, okay, so yes, then there must exist a point where the derivative equals 1/2. But that would be a mistake. But the mean value theorem is not applicable, however I spell applicable, to g prime on the interval -3, 7, because well, if we were trying to apply the mean value theorem to this g prime, what are the conditions of the mean value theorem? Well, the function needs to be continuous and differentiable. Is g prime differentiable? It's just not. And so mean value theorem is not applicable to g on -3 because g prime is not differentiable everywhere on -3, 7. For example, g double prime of 1, does not exist because sharp or something like that. Okay, so they don't give they don't ask for a full justification. They ask sort of why or why not. So why or why not means is explain your reasoning, and the reasoning is to run it back. The reasoning is, dude, this g prime function is not differentiable at x equals 1. We all know that. This is a sharp, pointy thing, and I could go into more detail if I wanted. The derivative of this function from the left would be 1/2, and the derivative of this function from the right would be, I guess that's just -1, right? Yeah. And so therefore g prime is certainly not differentiable at 1. Since g prime is not differentiable at 1, it's also not differentiable at -1 or 4. That means that this function g prime is simply not differentiable on the interval -3, 7, and so it would be inappropriate to apply the mean value theorem to g prime and conclude that somewhere the g prime had to be 1/2. And that's all they're asking. Does the mean value theorem guarantee that somewhere g double prime is 1/2? And the answer, no. But weirdly, in fact, there are places where g double prime is 1/2. On the interval from -1 to 1, this g prime function has slope 1/2. So in fact, for every point on the interval -1, 1, g double prime is 1/2. So it's not that the function doesn't have a place where the second. It's not that there's nowhere where g double prime of c is 1/2. It's that that happens sort of by accident, but not by the mean value theorem. So the mean value theorem does not guarantee that there's a place where g double prime is 1/2. But by the way, there are places where g double prime is 1/2. You don't need to say that, but I think they put that in there to test you or something. Okay, woo! Good, hopefully that was clear and didn't take too long.